Hi, thank you for viewing this presentation. Insulin pumps are effective tools for the precise control of glucose levels for people with type 1 diabetes. Unfortunately, many design and usability challenges still exist with these technologies. We investigated current shortcomings and limitations through survey, interviews, and participatory workshops. Our findings revealed issues with current technology including wearability and accessibility in public, operation while performing demanding tasks, interruptions during social activities, continual maintenance, interface operations. Using the data from our investigative work, we produced design criteria to develop a novel wrist-worn interface and separate pump design for a closed-loop system. We then evaluated the design through remote usability testing sessions. Our study aspires to inform the future design of insulin pumps that enable people with type 1 diabetes to maintain better control of their glucose through consistent interactions with these tools during their everyday activities. A 12-question survey was dispersed to several Juvenile Diabetes Research Foundation or JDRF online forums, which garnered 105 responses. In a multiple-choice question, respondents were asked to rate 4 features they would like to see in a new insulin pump design from most to least important. Small wireless controller was chosen as the top-ranked feature. 79 respondents gave feedback in the open-ended questions. We organized all of the answers into affinity diagrams to distill our insights. 18% of the respondents expressed feelings of insecurity or inconvenience when interacting in public situations. 33% mentioned challenges of interacting while performing demanding tasks, such as attending work meetings, exercising, or driving. And 26% of the respondents mentioned pain points accessing pumps worn in discrete locations, like under skirts or attached to undergarments. The most frequently discussed feature from the open-ended question, "What new feature would you like to see in a new insulin pump?" was to control pumps from a smartphone app. Respondents also suggested redesigning the pump's physical form, streamlining navigation, and designing better alerts and feedback. We conducted interviews to further explore the interruptions in social settings and performance of demanding tasks suggested by survey data. 7 participants were recruited through JDRF corporate offices and a JDRF Facebook group. Interviewees included 5 females and 2 males who use insulin pumps and continuous monitors, or CGMs. Interviewees mentioned receiving unwanted attention due to their pump controllers being confused with smartphones, or as a result of needing to interact with pumps during social situations such as attending religious services, job interviews, or formal meals. They also mentioned difficulty interacting with pumps while performing demanding tasks such as taking tests, during exercise, or while driving. Of the survey respondents who discussed demanding tasks, 27% specifically mentioned driving. 4 of our interviewees admitted to needing to interact with pumps while they were driving as well. Our findings relating to participants' feelings of insecurity and inconvenience were complementary to other HCI studies that investigated how people living with type 1 diabetes conceal devices in social situations to avoid embarrassment or even stigma, or show off devices as a way of spreading awareness. In both of these cases, living with insulin pumps has an effect on social interaction. After interviews, participatory workshops were held with 3 college students who use insulin pumps and CGMs. The workshops consisted of 3 activities: a mind map activity, collage exercise, and a design session. Participants used sketching tools and clay to design concepts like a rounded patch pump that could be worn without catching objects, a concept that sends important data to a social network of friends and caregivers, and a 2-part refillable patch pump CGM to reduce the number of devices attached to the body. We developed an interactive design strategy to guide the interface design process and address participants' pain points relating to interacting with pump user interfaces. One strategy guideline specifies tasks should be easy to accomplish in as few steps as possible. Our research showed that pumps often require an excessive number of steps during operation, as expressed by 14 survey respondents. The strategy also recommends limiting the number of visual elements present on the display. This is intended to reduce the amount of time needed to interpret content, which may help lower cognitive load, especially during demanding tasks. We designed a concept insulin pump to provide a contextual system for a new interface to operate within. Since our research found that participants desire control from smartphone applications and remote devices, our pump concept needed to facilitate remote interaction. A patch pump was chosen as the ideal form since patch pumps typically require remote controllers. The design features a main body and holster. The pump's two-part construction and rounded form were also derived from the participatory design workshops. Many participants expressed desires to control pumps from their smartphones. Unfortunately, no commercial mobile applications designed to control an insulin pump have been approved by the FDA to date. Because the FDA has not yet approved of a smartphone app for controlling pumps, a wrist-worn controller arrived as the ideal form for a dedicated medical device due to the familiarity of existing wrist wearables. The final interface concept features two identical mechanical buttons and a trackpad. The buttons function as a selection and back button, while the trackpad is used for swiping through menu items and scrolling numbered field values. These design features aim to reduce the amount of time required to interpret display elements, minimizing interruptions while performing demanding tasks or engaging in social activities. Once the controller was designed in CAD, we developed a smartphone-based interactive prototype for user testing. The prototype incorporates user flows for primary functions of an insulin pump, which helped to ensure that a functional pump interface could work using two buttons and a trackpad as the input method. 7 participants were recruited through a JDRF Facebook support group, including 6 females and 1 male. They were advised to use a think aloud approach for the entire session, talking through everything they saw and interacted with. Tasks included evaluating CAD renderings, evaluating the CGM interface design, and programming a meal bolus. Participants reviewed contextual CAD renderings of the controller to visualize the wearing experience. All participants supposed the arrangement of the buttons and trackpad would be easy to interact with. 2 users felt the design would reduce the number of devices to carry, especially for those who use a PDM-style controller with their patch pumps or need to use an extra bag or purse to carry devices. The prototype's continuous glucose monitor interface contains several elements that communicate glucose levels. Elements include the numerical readout, which gives the exact glucose number, and the arrow indicator, which moves up or down and changes color based on glucose levels. The arrow indicator also points up or down based on glucose trajectory. Participants evaluated the CGM interface depicting 5 scenarios showing different glucose levels. As each scenario was presented, participants were asked to examine the CGM and explain what the interface is communicating. All users recognized the CGM's visual elements in the following order: numerical readout, arrow color, arrow location, and arrow orientation. Programming a meal bolus was tested since this is one of the primary functions of an insulin pump. Participants were asked to program and deliver a meal bolus of 15 carbohydrates. This task was evaluated by measuring completion rate and number of errors made. 4 of the 7 participants were able to complete the bolus without instruction. Most participants gave notice when they saw that the prototype was showing a delivering bolus status. 1 participant was thought to have completed the bolus section, but was the only participant who did not communicate that they completed this task. Only 2 errors were communicated while testing the bolus section. For instance, 1 participant accidentally selected the suspend menu item, which stops insulin delivery. They were quickly able to resume delivery and go back to the bolus section without further instruction. Our user-centered approach with people in the type 1 diabetes community enabled us to thoroughly explore the pump human design space. We obtained valuable insights from testing the digital prototype. Participants performed most interface tasks quickly without error. Many participants were also vocal that the interface was intuitive to navigate. We also found that the design's buttons and trackpad are effective input modes for navigating the controller user flows. Participants showed acceptance of the watch controller concept as a convenient option for interaction since it is primarily worn on the wrist and not stored in a pocket or purse, making it readily accessible. Even though the controller design is a novel concept for a pump interface, participants felt it would be acceptable to wear given the current market saturation of smartwatches. In conducting our background research, we were unable to find a dedicated wrist-worn controller targeted at the type 1 diabetes community, supporting the notion of the watch controller as a key result from our exploration of the pump human design space.